Right, hello to everyone. Welcome to this NPTEL course on Advanced Reinforced Concrete Design. We will start with this first module, but we will be having this module in two parts. The first part is going to be introduction, and the expected learning outcomes from this part is basically, the student should be able to explain the history of concrete and reinforced concrete, how it has evolved for a period of time, and explain different types of reinforced concrete systems. We have different types of reinforced concrete systems, starting from plain concrete, reinforced concrete, and pre-stressed concrete. So briefly, we'll talk about that, and then one should also be able to discuss the advantages and disadvantages of reinforced concrete. Okay, and the student should also be able to explain the influence of cement production on sustainability. Now, there's a lot of emphasis on making the construction more and more sustainable, and so we'll briefly talk about that. And we'll also discuss the future of cement and concrete construction in general. Right? Okay, so we all use concrete in day to day life, and you know that concrete is one of the most widely used materials worldwide. And the statistic tells you that on an average, more than 2 tons per year is produced for every man, woman, and child on the earth, and making it is used second only to water. So you can see is one of the man-made material that is mostly used by human beings. And we use it for a variety of purposes, like the one that is shown here. And you see a nice bridge that is shown here, which is an access Praise Parkway Bridge in Franklin in the US, right? And in India also, we have built beautiful structures like the one that you're seeing here, the Lotus Temple, which is in New Delhi, right? And then in Mumbai, I think our metropolitan cities are also seeing now more and more use of high-rise construction. And one example that I see here is a three towers, which is called World One in Mumbai. Okay, so that is also made of reinforced concrete. Of course, concrete we have been using it for pavement construction, and the one that you see here to construct beautiful dams and so on. So it has become over a period of time very indispensable material. Right. Now let's talk about the history of reinforced concrete and how the concrete has evolved over a period of time. I think people have been using concrete from time immemorial, especially Romans, and then even before people, there is a documental evidence that people have used. I'm going to talk about only what has happened in the last 3 centuries, right? Um, John Smeaton, he was a British engineer in 1800. He found that when he mix lime and clay, he can make uh, cement out of it, which is having a very good binding capacity. In fact, and also it was not dissolvable in or water. Okay, so he was exploring this for constructing lighthouse. In fact, he did construct some lighthouses using this material, right? And then in 1824, Joseph Aspidin, okay, he invented this Portland cement. So he realized that when you burn the limestone and clay together, you form a clinker, and that basically gives the very good binding property, and also it doesn't really becomes insoluble when water is in contact with that, right? So 1824 was one of the major achievements in terms of modern cement invention in 1824, which was done by Joseph Aspidin. Then several people started exploring using this modern Portland cement for constructing. Okay, and in fact, concrete construction were constructed before, but in 1864, in fact, Joseph Monnier, he is a French florist. Basically, he was a gardener. He was making a lot of flower pots, and he was finding that the flower pots were getting cracked quite often. Right, so he used wires and used the cement to make concrete flower pots which are also reinforced with steel wires. And he found that the cracking was very limited and the performance of the flower pots were really good. Right. So in fact, he is considered to be one of the pioneers in inventing the reinforced concrete. And then Hennebeck, he followed the inventions of Joseph Monnier, and he invented this Hennebeck system, which is basically resembles even the modern day construction where we use stirrups and where we use longitudinal rebars wherever tension is possible from external loading. So in 1892, Hennebeck, in fact, he patented this concept of reinforcing and constructing buildings using reinforcing steel and cement concrete. And another major invention come in the year 1933, where Fresnel is also called as father of pre-stressing concrete. We all know that concrete is strong in compression but weak in tension. So Fresnel invented method of putting concrete under compression by pre-stressing so that under external loads they're not going to crack. Okay. So we can design the amount of pre-stressing to make sure that the reinforced concrete elements are not really going to crack. And it really changed the way we construct long span structures using concrete. And in 1957, in the UK, Monsanto, there is a company, they built one small classroom building using glass fiber reinforced polymer material. Okay, this is about 1950. In fact, right after World War, there are a lot of emphasis on developing very lightweight materials from aerospace applications point of view. And for buildings also, this was one of the earlier attempts of building a small classroom using glass FRP based system. Because the reinforced concrete system, though we get a lot of advantages, but the reinforcement inside the concrete corrodes, so it affects the durability if you're not very careful enough. So this glass FRP was one of the pioneering attempts to showcase that these modern materials also can be used for construction. Then around 1970s, people invented this high performance concrete with using a lot of supplementary cementitious materials, and they were able to get higher strength and higher durability performance and so on. Right? And around 1994 in the Europe, people invented something called ultra high performance concrete, which is being very widely used across the world now. You can get strength in the order of 150 to 200 megapascal, and with excellent tension and flexural strength. Again, the reinforcement pretty much remained either deformed steel or a pre-stressing steel for pre-stressed concrete. Very recently, people also developed fiber reinforced polymer based tendons for using it as an internal reinforcement for making concrete so that we can tackle the corrosion in a better way. So this is the brief history of how the concrete has evolved over a period of time. Now, this is one of the very famous structure you all might have heard about it. This is the Roman Pantheon, or the one that you see here. It was built in 126 AD. In fact, it had about 144 feet span, which is actually considered to be one of the longest span till 19th century. They built with different lightweight aggregates like kumais and broken bricks and so on. As they were approaching the top of the roof, in fact, they were using lighter and lighter material. And they used Roman concrete, which is called as opus cementitium, and this is the one that used in pretty quite a bit in the Roman Republic and throughout the whole history of Roman Empire. Okay, and in fact, this concrete has very good hydraulic setting properties, which is very similar to the modern day cement, which is the Portland cement. And with respect to concrete, we know that concrete is quite very good in resisting compressive forces. However, in construction, usually the flexural members govern the design, and we always want to have large column free space. So when you try to span a structural element, the limitation in capacity is actually controlled by the tension capacity, right? So, for example, this is a simply supported beam that is subjected to a point load that you see here. And if I take a section and if you look at the stresses, if it is a plain concrete beam, you know that from simple bending theory, you're going to have compression at the top and tension at the bottom, and it is going to vary linearly. Strain is going to vary linearly, and because this material is going to behave in a linear elastic fashion until cracking, so the stress is also going to be varying in a linear proportion with high stresses at the extreme fibers. And the moment the bottommost fiber reaches its tensile strength, then you're going to have crack. And as soon as the crack is formed, you do not have any reinforcement that is going to arrest the crack, then this beam is going to fail. So usually the tensile strength sigma T is considered to be roughly about 8 to 15 percentage of your compressive strength, which is F prime C. So we are talking about 8 to 10 percentage only. Okay, 8 to 10, 8 to 15 percentage is what we are talking about. Okay. So pretty much, if you're taking about 40 megapascal concrete, then you're going to have about right. So you're going to have about 3 to 4 megapascal of tensile strength. So as soon as it reaches its tensile strength, it is going to crack in tension. Right. So this is one of the earlier systems that I explained in the previous slides, which was invented by Hennebeck. In fact, you can see you have nice longitudinal bars, and also you have bars going over the top of the support, and you have nice stirrups here, right? So it pretty much resembles whatever even what we are using today, right? So he was one of the pioneers in pushing this reinforcing systems in modern building construction in the beginning of 20th century. In fact, the first building was erected in the UK with this system in 1897. It is called as the Weaver Building, and he also started exploring making floor slabs in 1879, and then later on progressed to make a complete building system. It was also patented in the year 1892. Okay, so you can clearly see the nice arrangement of reinforcement inside the concrete, and wherever the concrete you're going to develop tension, and the reinforcement was provided. Now, so coming to the properties, now we have briefly discussed the history, some of the important developments that happened over a period of time. Let's look at the characteristics of the reinforced concrete. And as I've explained you, concrete is having very poor tensile strength. It is very good in compression. So tensile strength is the weak link, right? Usually it is about 8 to 10 percentage of your compressive strength. And wherever you're going to develop tension, so you're going to put steel reinforcement that is actually added to provide tensile strength. But again, steel is good both in compression and tension. However, if you're not careful in compression, the steel can buckle. So, especially when you're using it as a reinforcement in column members, the longitudinal bars, we have to make sure that the transverse reinforcements is provided at a particular spacing so that it is not going to buckle and lead to sudden failure. So that is a problem. So then people thought, okay, let me combine the best properties of concrete and steel and then make them together and make a reinforced cement concrete, which is actually a combination of concrete and steel. And wherever you're going to develop tension from your structural analysis, you start putting steel to tackle the tension. Now, as you can see, this is a simple cross section. What we do analysis, right? You have concrete and steel, then you reinforce it. You can reinforce it either at the bottom or at the top or at both locations, depending upon your design requirements, right? If you put only at the bottom, we call them as singly reinforced section. If you put at both sides, we call them as a doubly reinforced section. We will get into when we go for singly reinforced, when we go for doubly reinforced, all those things in the later modules. So in summary, the RCC, the compressive strength is actually provided by concrete, and tensile strength is actually provided by steel. So both of them, they really work together, and there is a synergy, and they perform very well, right? So now let's move on to how the reinforced concrete, for example, if I take a case of a building, how the structural elements are arranged and how they are performing together to meet the design objectives. Right. So usually in a building, we all know that we have slabs. Okay. For example, if you look at in the second floor, what you see here, the second floor is supported by a slab. On the bottom you have something called joist are small beams which are spaced at certain spacings, usually about 3 feet or 4 feet or 5 feet depending upon the requirements, right? And we apply the loads on the slab. Okay. Okay, I am talking about gravity loads, but when you have a lateral load, that again we'll talk about. Lateral load can be from wind or from earthquake, right? Then you need to have a lateral force resisting system. If it is a simple building only with moment resisting frame, that can act as a gravity load resisting system as well as a lateral load resisting system. But if you're going taller and taller, you need to have other specific systems that has to be used. Okay. So for example, in this case, for a gravity load, for simplicity, we apply the loads on the slabs like what is shown here, right? And then the slabs transfer the load to the joist. Okay. These are called as beams in this case for the particular floor, right? And at the sometimes at the edges, the joist may be also be connected by some beams, right? So the slab transfer the loads to the joist, then joist to the column, then column to the foundation. So this is the load path. So if you look at it in the first floor, slightly we have a different system. Okay. So we do not have joists, but we have beams. Okay. So the slabs are transferring load to these beams, and then in turn the beams transfer the load to the column, and then column to the foundation. And again the foundation also has to transfer the load to the soil below. Okay. Again the soil also should have adequate bearing capacity, otherwise we can have a foundation failure. So these are the two examples. You can see the various elements you also see here. This is, I think, in the basement you see here, the slab is supported directly on the soil, subsoil, right? That's why we call that as a slab on grade, because the loads are directly transferred to the soil, right? And then we also have, because you have soil that is retained here, so you need to have some retaining walls. So these are called foundation wall or retaining walls. And you also have other structural elements like staircases, and then you have landing slab and so on, right? So in general, in a building, for a gravity load systems, you apply the loads on the slabs transfer the loads to the beams transfer the loads to the columns transfer the load to the foundation, and foundation transfer the load to the soil. So again, at each step, we need to make sure that the structural members are having adequate capacity. Otherwise, it's like a weak link theory. In a chain, when you pull it, even if you have one link which is weak, that is going to fail, then you will not be able to transfer the force. So we have to make sure that at all levels, we design it adequately so that your design objectives are satisfied. Now, this is another system which is nowadays in the modern day construction quite commonly used. You can see here that in this system, we have slab that is directly connected to this columns. Okay, you can also have another variation of this where the slabs again connected to the column here. For example, if you look at it, that however, above the column, what you have is a flaring increased thickness of the column, which we call that as a column capital. Then you also have additional thicker element like this, what you see here, right? So this is called as drop panel. Okay, and again we need to make sure that we provide enough dimensions of this drop panel so that they can also help in resisting the negative moment that is going to come at these locations. And mainly we provide this capital and drop panel to make sure that the slab is not going to punch through the column. In fact, when the slab is punching through the column, it's called as punching shear failure, which is a very brittle mode of failure. We need to be very careful. In fact, in flat plate, this is one of the things that we need to be very careful as a design engineer, because um, the slab loads are directly transferred to the column over a short area. If you're not very careful, then you can have a punching shear failure. So in the later modules, we will talk about how to design for this slabs for two-way shear and one-way shear and so on. But you have to be careful. But the advantage with this kind of systems is, you get rid of the beams. So from aesthetically, it looks very pleasing. And for example, if you have a height restrictions in terms of total building height, then if you are able to remove this beams at each floor level, then in fact for the particular height you can construct additional floors. So that is from owner or client point of view, it is going to give you a lot of advantages. So that is the reason in the modern day construction usually these flat plates are post tensioned. They're called post tension slabs, and if you design it properly with adequate lateral load resisting system. In fact, this would be an attractive option for spanning the slab. Okay, so for building, we looked at how certain things are arranged, structural elements are arranged to transfer the load. Now, let us look at here again. For example, this is again a building structure, and this building, if you look at it, basically is going to have G plus 4 stories that you have, ground plus 4 stories, right? And you have arrangement of columns and beams in both directions. Okay? Usually, this is a moment resisting frame system, right? And the end, sometimes you also have walls like this. Okay, wherever it is possible, you can have these kind of walls which are called as shear walls. Okay, which is usually made of reinforced concrete, and it can give very good rigidity for taking care of the lateral load resisting system. And if you look at this structure, and if you take the plan, a typical floor plan, this is how it's going to look like. You have beams going in both the directions, right, and in each direction actually we do the analysis. Okay, and they're also connected to column. So if I take only at this location, for example, and look at this elevation, I'm looking at only this frame. So you see here the loads get transferred to this frame, right, like this. For example, here we have assumed it to be uniformly distributed load. Usually in buildings, dead load and live load, based on the tributary area of that particular structural element, we calculate, and then we assume it to be uniformly distributed for gravity loads, particularly, and then we can do the analysis of only this plane frame. Okay, so this is from typical structural analysis. So if you know what kind of loads that you're designing for, usually design codes will help you. For example, IS 875 will part 1, part 2, part 3, we have different parts. So that gives you guidance, okay, what kind of loads that we need to consider. So depending upon what we have considered, then from simple tributary area, we can calculate at each floor level for that particular frame how much load is that is getting transferred, right? So so this is a plane frame analysis. So like this, we can select critical frames which are having larger tributary area and design for it, and then you can optimize your design. So in fact, before the advent of your computers and modern software programs, people used to do this, using hand calculations in this same way. You basically discretize this structure as plane frames in two orthogonal directions, and then you design using your conventional matrix method or your moment distribution method or simplified methods that you must have learned in your structural analysis course, right? So this is the thing, right? So as I've told you, in a building, typically we have two types of load resisting systems. Gravity load resisting system, which takes care of the dead loads and live loads and superimposed loads that what we are putting on the system. These are called as gravity load system. And we also have lateral loads that are coming from wind and from earthquakes and so on, right? So that also has to be designed. So sometimes the same structural system will do the work both as a gravity load resisting system as well as a lateral load resisting system, right? But sometimes specifically we design the connections in such a way that certain systems will take part only for gravity load transfer, and then certain systems which will be heavier, that will basically take care of the lateral load system. Okay, so for example, this is the way that a building, for example, let's say if I look at the facade of the building, the what you see here, okay, right? So it is subjected to some wind pressure, and then the facade panels, cladding, that will be subjected to this wind pressure, but these cladding panels are also connected to the columns and frames. Okay, so depending upon the tributary area of the cladding that is supported by a particular frame, and depending upon the wind pressure that is acting on the cladding panel, now I can basically find out how much is the load that is getting transferred to a particular frame. Okay, right? So usually either you are doing reinforced concrete cast in place construction, or in precast we make sure that we develop rigid connections. Unless explicitly it is designed as a shear connection, then you transfer only shear. Right, most of the time in cast in place construction they are all rigid connections, right? So the columns and beams are all poured together with reinforcement continuity. So you make sure that both the columns and beam are going to rotate by the same magnitude. So you're going to have a rigid connection. So we call that as a rigid moment resisting frame if it is designed properly. Then you take a frame and you found out based on the tributary area how much the pressure that particular frame that is going to take. Then you can do the structural analysis for that. Now you can do the same frame can also take the gravity load resisting system. So you can now you get one analysis from gravity load, another analysis output, that is bending moment and shear forces and so on, from your lateral load analysis. Then you combine them based on the load combination that is suggested by the code. Then you design the particular members, right? Similarly, you can also have these kind of shear walls that will basically take care of all the things, all the lateral forces, because they have very high in plane rigidity, and it is going to basically, if I take two springs and if I connect them by the same in a parallel connection, right? If you have a heavier or stiffer spring, that is going to attract all the force. So in the similar way, though if you have a shear wall frame like this and a moment resisting frame, if your shear wall is quite rigid and quite stiff, then that is going to attract all the forces. So that is the way we design for high story buildings, and making sure that we put shear walls in such a way that it is going to relieve the lateral load to the moment resting frames. So both of them will act together. So as I told you, so if you connect two springs in parallel, the stiffer spring will start attracting more force. So then it will relieve the forces that are going to the other gravity load resisting systems.